Okay. So thanks for coming. I'm Pablo Lara, by the way. I know most of you, I think, but I have a lot of new faces that I'm glad to be here. So first, I have to thank my advisors. That is the first time that is here. The three of them are here. This is the first time. Jean-Paul Ampuero, Ensemble Blettery, and Adolfo Insa is visiting from Peru. So I'm glad to present to you the implementation of the Peruvian earthquake early warning system. So first, the problematic of Peru is because they have a lot of specific hot spots where a large earthquake can occur. And this work from Villegas showed to us that in this part, for instance, in Lima, an earthquake of magnitude 8.8 can occur in these years. He forecast when could happen an earthquake. So there are not only in Lima, in the south of Peru, there are another spots that can occur an earthquake. So for this problem, the government of Peru, and through the IGP, the Instituto Geofísico del Perú, and INDECI, Instituto de Defensa Civil, IGP is the Geophysical Institute of Peru, and INDECI is the Emergency Management. And through them, create the SASPe project, that is the Peruvian Earthquake Early Warning System.
Oh, there is a pointer against the wall there.
Ah, thank you. Where is it?
No, let from the street.
Ah, here. Okay, yes, I was looking for that. Thank you. So, okay, so there are two components. The first two are in charge of IGP, that is the know of the earthquakes in Peru, how the knowledge of the earthquakes in Peru. The second one is the monitoring and the alert. This is the algorithms, that this is my work. Then when we have the alert message, they send to the INDECI, who is in charge of broadcast for all the people in Peru, the alert message. And not only that, also INDECI has the duty of train the people to interact with SASPe. So these first two are completely done by IGP. INDECI is nowadays creating the stations for zonal alarms, and also creation of the development of mobile application for broadcast alarm. So on average, this project will benefit more than 18 million people. So you want to looking for more information, you can visit this website. So as I said to you, the second component of the SASPe is the implementation of the algorithms. The algorithm that we create with my advisors is called E3 warning system. That is the Ensemble earthquake early warning system, starting from 3 seconds of record on a single station. This algorithm has three main stages. The first one is the detector, who is monitoring the continuous earthquake. If the detector trigger with a probability of P phase more than 80%, then it's carrying out a scanner. The scanner is a picker. From the 10-second windows of, let me put this. From the 10-second windows, this is like monitoring slightly 1 second. No? If a window trigger, then we analyze this window with a short window, just scanning very quick, very small, and the period of time 0.2 seconds, just to see the onset of the P phase. So this is the picker. The picker, the duty of the picker is to estimate the P arrival time. When I have the P arrival time, then we wait initially for 3 seconds to characterize the earthquake. This is the magnitude and location. But this algorithm has continuous update. Not only that, just for 4, 5, 6, or until 60 seconds, we can estimate the magnitude and location. But in Peru, we use just until 9 seconds because this algorithm is placed on the Raspberry Pi 4 device. That is a very, very small device that cannot storage a lot of models. So that's why we use just until 9 seconds. So just a very brief, very short resume of the E3 warning system. This is already published. E3 warning system is a model, it's the first model around the world that is completely based on artificial intelligence. So we trained the model with global data. This is the Stanford earthquake data set from Usabi, the Peruvian and the Chilean database, and also the Japanese data set KIGNet and KNet. So with this data, just this is a resume of that. The E3 warning system achieved 99.9% to classify between earthquakes and noise. And the peaker has a mean of almost 0 and a standard deviation of 0.14 seconds. So this is more than enough for earthquake early warning proposals. And also, using 3 seconds, this is the comparison between the estimate and the real. We can see that in 3 seconds there, after maybe 5.6 or 6, some fluctuations. That is completely normal because we have only 3 seconds portion of windows to estimate the magnitude. This is also the estimate of distance, depth, and this is the weakest link maybe in E3 warning system. It's the estimate of the bag azimuth. That is because it's very hard to estimate the angle with just one station. The error of this is around 43 degrees. Of course, if we have longer signals, the estimate becomes better. So you can look this part as is almost ideal, the distance, no? The magnitude as well is improved. But the bag azimuth is almost the same. So we compare the E3 warning system with maybe the most popular one, earthquake. There are another earthquake early warning system here. So this is the Tohoku earthquake of magnitude 9. We use the nearest station to the source. This is the source time function, the light blue. The dot light blue is the source time function, but shifted to the p-arrival time of this station. So just to for comparing the instantaneous magnitude. So the E3 warning system is the black line, and the fastest earthquake early warning systems here is E3 warning system and the E-LARNS. E-LARNS is the green one. The E-LARNS is an algorithm based off a network. Actually, all of these are based on a network station. The only one who is based on single station is the E3 warning system. E-LARNS is from the Shea Alert earthquake early warning system from USA. So we can see that E-LARNS and E3 warning system start practically the same. And also, the E-LARNS saturates after 22 seconds after the origin time. But the E3 warning system is still increasing, the estimate is growing. And then follow the GMA, this is the GMA estimate of Japan. And finally, is almost at the same accuracy as earthquake early warning based on GNS data. That is the G-LARNS. This is before, and also the new one, earthquake early warning system, that is a PEXNet. No? PEXNet is from elastogravity signal. No? So this is maybe the figure that I have that I can compare with most earthquake early warning systems here around the world. not only that, if you, by the way, if you want to see this paper, these are really published in GGR Solid Earth. And not only that, is proved in another country, that is the Montenegro thesis from the Universidad de los Andes, that he used the E3 warning system to estimate the source characterization using Colombian seismograms. And also, Eric Calais, we as well, because I collaborate with him in a little part of the beautiful paper, we characterize, we use actually the E3 warning system detector and the Omori law to estimate the daily afters after the main shock of the earthquake of 2021 of magnitude 7.2. We can see in this figure, for instance, that with just 12 hours after the main shock, the catalog and the estimate from the E3 warning system detector is almost the same. After 96 hours, of course, they are practically equal. So this is just to show to you that E3 warning system is global. We can apply anywhere, and maybe this is the most important difference between the E3 warning system and the URDAS from Nakamura, because both are based on 3 seconds. Both have a picker, a detection, and source characterization estimates. But the good point from E3 warning system is that you can apply globally. The URDAS have some overestimations if you apply them from another country that is not Japan, that you have an overestimate between 3 and 6 to estimate in magnitude estimate. So that's maybe the most important difference. Also, we apply this to another recent major earthquakes. That is, we can see in the first column the name of the earthquake. We use the closest station. This is the true magnitude, and this is the magnitude based on E3 warning system algorithm, using just 3 seconds and using 9 seconds. And the most important column for the user point of view is the last one, because in each location in this column, they have fatalities. So we, based on the E3 warning system algorithms, we can see that we can give to the user, in the most of cases, a positive user lead times. But also we have a little location that we cannot reach that. For instance, in Susuk, that is super close to the source, or in Marrakech, because the earthquake, the station in Marrakech was like in this part. The source of the earthquake was in this part, and Marrakech is in this part. So I have not a closer one station around this earthquake. And the most recent one is in Taiwan. In Taiwan, I applied that just for curiosity. This is the closest station that is just 6 kilometers from the source, and the E3 warning system in 3 and 9 seconds is 6.5 and 6.9. I know that in this part, in 3 seconds and 9 seconds are the same. The early warning system in Taiwan is, if I am not wrong, 6.2 and 6.8 in comparison with the E3 warning system. So this is just an abstract of how E3 warning system can be applied. But now let's back to the scenario of Peru. We install them in each station in Peru. There are 110 stations along the coast of Peru. And this station is grouping by 10. 10 stations send the information, each one send the information to the operational regional centers that is called cores. This is the green one. There are 10 cores. Each core manages 10 stations. So from the cores, if the algorithms send alarm, the proposal of the cores is to send this alarm to the indices. Indices is in charge to broadcast the alarm to all the people. So this is a typical station of SASPe. This is a lighthouse. Inside this station, we can see the devices. This is a stop motion accelerometer, a recorder, a digitizer. This is a white box that I'm going to explain what this is inside. The antennas, the zonal panel, and batteries. No? Inside the white box, we install the algorithm. This is a Raspberry Pi 4 device. It's not a Raspberry Pi, by the way. It's just a Raspberry Pi 4 single board computer. Inside this, we install the algorithm in each station. So we have 110 Raspberry Pi 4s along the coast of Peru. By the way, ignore this picture, please. So this Raspberry Pi 4 send alarm to the cores, and in the cores we broadcast to all the people. There are two main broadcasts. One of these is a sonar alarm, with high decibels to just alarm the people, and the second one is with mobile devices. No? So in short, this is how SASPe works. There are a real-time seismic stream. If the E3 warning system detects the earthquake, they estimate a magnitude and location. With this magnitude, the government placed that if the magnitude is above 6, they have to emit the alarm to the people. So, what is the proposals of estimate magnitude and location? With this boat, we can estimate the peak ground acceleration based on attenuation load. With the peak ground acceleration, we can estimate the alert radius. For SASPe, the alert radius is until the people feel the shake of 5% of G. G is a gravity signal. So we have this is a theoretical alert radius. But because E3 warning system is not, the residual is not zero, they have some errors in magnitude and location estimate, we have to compensate these errors through a tolerance. A tolerance is how many kilometers we have to add to the true alert radius to compensate the errors in magnitude and location. So basically in derivatives, we estimate the tolerance based on magnitude, depth, and epicenter location. So this is the influence of epicentral distance in the tolerance. This is in magnitude, and this is in depth. So we can see that we have a lot of residuals that is influencing the alert radius here in the epicentral distance. So I applied a lot of methods to improve this, but I really found one method. Here we can see. Okay.
Sir,
yes.
Just a quick question, but I don't understand what you call tolerance.
Just
like
here?
Yes.
Yeah.
What is tolerance?
Yeah. Okay. That's a very important part. Okay. The tolerance is, for instance, if you have a magnitude 6 with an attenuation load, maybe you can apply a Shao attenuation load, you can find the alert radius is 100 kilometers for this magnitude and a specific location. You have 100 kilometers, right? But this is if you have the true magnitude and the true location. So because this system have an error, maybe in this position this is not the truth. maybe this here. So we have another circle. Just to compensate this, we have to add, right? We have to add a little more portion of that. If you learn maths, for instance, you can apply the PGA as a function of magnitude, depth, and distance. And then you can apply the partial derivatives in magnitude, depth, and distance to find this theorem. I'm not sure if this is okay. 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 So, okay. So I want to improve this part because it's for me it's very high. So because it's like twice the influence of the tolerance in magnitude. So to improve this part, I use the other station who already have the P wave when the first station have 3 seconds of the P wave. So if the first, for instance, in an earthquake, we use the first estimate with 3 seconds. So, but that not means that we can use just this one station. There are another station that may be triggered. We use this information to improve the distance. For instance, we can see that we can have 3 stations when the first station has 3 seconds of records. So we have 3 stations that maybe have a little portion of P wave. So we use the information of the P arrival time to improve the location. How can we improve the location with this piece of information? For the first station, okay, we cannot do anything. We have just the station and the estimate. Okay, that's okay. If we have 2 stations, this is a little hard maybe to explain. We have the first station, the estimate. Okay, this is the first one. The second station, we have the angle. But we have not the distance because we have just a very short P wave window. So how can we estimate the distance? The distance is velocity multiplied by time. The velocity of the P wave is the same for both. And we have the time because we have the P arrival time of the second station. So that leads in this line, we have the distance. Okay, so we have 2 possible locations. We average them, and the one who is closest to the intersection of the distance is the choice of the estimated. This is for 2 stations. From 3 stations, we just made the triangulation. The triangulation is simple. We have just the intersection of the circles, and for more than 3 stations, it's the same. So with this information, we improve the error of distance from 84 kilometers of intolerance to 43 kilometers. So it's 15 kilometers better. So with this methodology, we apply to the earthquakes in Peru. The E3 warning system detects in Peru in real time in more than 2 years of continuous data, almost more than 6,000 of observation regarding to almost 2,000 of earthquakes. This is the distribution of the magnitude, epicentral distance, depth, and azimuth that we detect in real time with the E3 warning system in SASPe. Of course, we have some false negative and false positive, but as the same of the original paper, the false negative is below from magnitude 4.5, so that not represent any damage to the people, and it's more around 100 kilometers. And not only that, we have some false positive, but the false positive, the maximum false positive is 4.5, so that not trigger the alarm of the SASPe. We have this a lot of false negative here below 4.5 because the high trigger of probability of 80%. We put that because in Peru, the noise levels around the station are very high. So we increase a lot the probability of detect an earthquake, a P wave, to 80% because there are, as I say, it's too high. So that's why we have a lot here. In 2 years, we have like 500 of false negatives here. So this is the results of the SASPe in 2 years. This is for low magnitudes. We have a little bias. The original paper of the E3 warning system is the same. So we have here the line is like a line estimate, and here is the important thing for SASPe. There are just 2 earthquakes that is above magnitude 6 in SASPe. But these 2 earthquakes, the SASPe estimate that these 2 earthquakes above magnitude 6. So for both of them, it's triggered. So that's a good point. And not only that, all the other earthquakes is below magnitude 6. And the estimation is below magnitude 6 as well. So that leads that we have no false positive nor false negative in the alarm. And the location, we improve, as I said before, we improve the location estimate using a single station and the same single station, but with the information of the little portion of the P wave around the station. So this is the location improves. So, okay, we have the magnitude, we have the location. Now we can apply the alert radius. This is the attenuation law using Chow. For instance, if the magnitude is 6, this is magnitude 6, the blue one. If the magnitude is 6, we have to alert the people until 5% of G. This is 5% of G. So the alert radius, the theoretical alert radius is 100 kilometers. But we have some tolerance. The tolerance for magnitude 6 is this. This is based on 3 seconds. The first estimate, we have to add 83 kilometers to the 100 kilometers. So we have that leaves 183 kilometers to alert people. So I want to show how it works in real time in SASPe. This is not a magnitude 6, but this is the largest one that I found in Peru. This is a 5.4 in 2 years of data. The SASPe triggered this. The SASPe doesn't trigger, but I simulate that this triggered. That is 5.4. This is the closest station. The triangles is the station of SASPe. The circles is the station from the national network of Peru. And you can see maybe some larger triangles and larger circles. These larger ones means that in this place there are people feel more than 5% of G. So, for instance, this circle in blue means the theoretical alert radius, and the purple one means that is the alert radius plus the tolerance. So the colors means how many seconds the SASPe gives to the user. In this part, we can see that for people living on the beach or in the coast, SASPe can give from 0 to 2 seconds. That is too short. But for other location, maybe here in Lima, because it's all this in Lima. Lima is housing 11 million of people, so it's a lot of people living there. So this is very important very important earthquake, because it happened in Lima is like is the third part of Peru is living here. So in here we can see that we can give to the people in Lima from 0 seconds to 20 or maybe more here. And also, we can see if, because of the tolerance, we can see that there are some part that people feel 5% of G. What happens if we don't use tolerance? So these people doesn't receive the alarm. But because we use tolerance, we can alarm these people. And finally, and this is maybe the last slide, we assess the blind spots in Peru. So imagine you live here. So we apply synthetic earthquakes around along the subduction zone in Peru, all the earthquakes, and the earthquake who arrives you the fastest one, this is the earthquake that we choose to have the user alert time. So this is the worst possible scenario. It's just to see if there are some blind spots in Peru, and there are in fact. We can see here in this part, this is the greatest part maybe. The people in Piura, in the north of Peru, cannot have the alarm. So the S wave arrives then faster than the alarm. So that's the meaning of this white spot, the blind spot. Also in Ica, we can see some blind spots here. But even that, this is the worst possible scenario, and even if happening this for people that live farther away, is useful, the algorithm. So with this, I'm going to finish this presentation. And if you want to take a look of this algorithm, you can take this link. Thanks for your attention.